Hello everyone, I'm Wen Huili from Tianjin University of China. I'm one of the organizers for this track, Extended Monocular Image-Based 3D Object Retrieval. First of all, I would like to introduce our team. Our team is from the Institute of Television and Image Information, which is supervised by Professor Yuting Su and An Liu. Our research areas include computer vision and machine learning, multimedia understanding and retrieval, and so on. Here is my outline. Next, I will give the introduction about this track. This track aims to retrieve the relevant 3D objects by using the real RGB image. The motivation for this track is that it has wide related applications such as automatic 3D content generation, augmented reality, virtual reality, and so on. Now, there are a lot of 3D retrieval algorithms by using 3D model as a query. However, there are two limitations. It is difficult in getting the query 3D object for consumers in real applications. The second is the query 3D objects with complex structures requires large storage space. So we want to develop the image-based object retrieval methods. The challenges for this task are that there are lots of related benchmarks, and the gap between 2D images and 3D objects makes the problem extremely challenging. We collected the dataset named Extended MI3D Object Retrieval, which contains two domains. One is the 2D one is the 2D RGB images from the ImageNet, and another is the 3D objects from the existing 3D datasets, for example, NTU, PSP, ModelNet, and SHREC. We also project the object into multi-view image set, so there are two formats for each object. Here are the details of the dataset. It has 21 and 40 categories, and the data formats we provided are JPEG for 2D image, OBJ for 3D object, and PNG for 3D views. We use half data as the training set with labels. The remaining data is the test set without labels. In this track, participants can use one domain or two domains labels of the training set to learn the image and object representation. Following this reference, we employ 7 criteria to evaluate the retrieval performance. In this year, 8 organizations registered our track. However, due to the impact of the new coronavirus and some reasons, only 2 teams successfully submitted their results. The detailed information of the participants are shown in this table. Okay, next part is the methods. There are totally 3 methods, and all these methods use the labels of 2 domains to train the network and learn visual representation for both image and objects. The first method is semantic similarity-based 3D object retrieval from monocular image, which is submitted by Tianjin University of China. They first extract the probabilities of 2 classifiers as the feature of image and 3D models. Then they select the top 5 or 8 maximum values from the probability vectors as the feature, and measure these features by using cosine distance or vector multiplication. Finally, they sort these similarities and obtain the final retrieval results. This is an experiment that they finished the 2 tasks and provided 10 submissions with different similarity measure strategies for each task. The top key means that the highest key values in 40 dimensions are retained and the other dimensions are set to 0. Here are the performers for 21 categories. The fifth strategies get the best performers, which shows the effectiveness of vector multiplication with normalized scores. And the results on 40 categories show that this method has good adaptability to the increase of categories. The second method is the 3D object classification with view set from University of Science and Vietnam National University. The overall structure is shown in this figure. They also train two classifiers to obtain the representation of image and 3D object, and then they use different strategies to measure the distance between these two features. In this method, each 3D object is represented as a collection of unordered 2D views, and they do not explore any spatial relationships of 3D model. Then they use the attention scheme to encode these features and adopt the average pooling to fuse the multi-view features, and then train the classifiers. This is experiment that the top two submissions use train model as feature extractors and utilize attention scheme to generate object embedding. Finally, they measure the similarity by using the different strategies. The third and fourth methods use fine-tuned models and feature extractors, and they also use different similarity measure to compute the distance. This is the performance. We can see that the third and fourth methods perform better in most evaluation criteria, which indicates that the fine-tuned models can obtain the discriminative features. The third method is the 3D object classification with view sequences. It also submitted by the University of Science and Vietnam National University. In this method, each 3D object is represented as a collection of sequences. Each sequence consists of topologically ordered 2D images captured from the different views. There are two ways to generate the collections. The first one is the left is, for example, the left setting only use 3 rings, and each ring contains of 12 views. The right setting uses 7 rings, and each ring also contains 12 views. This is view sequences framework. The view sequences are concatenated and fed into the attention-based bi-direction LSTM module to capture the important information. Then the sequences are averaged to generate the final representation. The table shows the different structure by using different feature extraction model, view sequences, and the strategies of similarity measure. This is a performance. We can say that VSQ 5 to 8 are better than the VSE S01 to S02. That shows. That's mainly because the VSQ explores spatial relationship among the views of the 3D model, which enrich the 3D model representation. This is a total cooperation of 3 supervised methods for 21 categories, the fifth methods get the best result. And for 40 categories, the last one performs best. The final part is the conclusion and the future work. Here is the conclusion. All methods developed deep neural networks to extract and fuse multi-view visual features for 3D object representation, which get better performance. The second is that all methods trained two classifiers and then use the probabilities of the classifiers to represent 2D image and 3D object. This way can leverage the huge gap between the two modalities. The extended MI3DOR benchmark also has potential for unsupervised learning tasks which has not been discovered yet. Therefore, this direction still needs more attention from researchers. According to our observation, in the future work, we plan to apply for new track or monocular image-based 3D object retrieval by enlarging this dataset with more 3D object categories and more 2D and 3D data. Next year, we will advocate unsupervised cross-domain retrieval methods for this task and advocate cross-domain learning between visual features of 2D images and spatial structure of 3D objects. So welcome your attention and participation in next year, and welcome co-organizers of this track for new data, new scientific problems. Finally, I would thank the organizing community of 3D shape retrieval contest and thank all the participants. Their contribution will certainly promote the development of this field. This track is supported in part by the other foundations. That's all. Thank you.